Good morning, I'm Manuel Zarzo, and in this Unit 7 about ANOVA, I'm going to talk about the orthogonality in designs of experiments, which is a very important concept. Good. This is a design. Okay, we have one factor which is tested with two variants, A and B. For example, imagine that this is like two types of catalyst. Imagine that we have a second factor which can be like the pressure. We have pressure equal 2, pressure equal 3, and then we have this third factor which can be like two different kind of suppliers or raw materials. Okay, so we have 8 trials, and imagine that we run the experiment, and this is the response variable, the 8 variables, the 8 values that we have obtained experimentally. Okay, so we have 3 factors, 8 treatments, 8 trials. But is anything wrong in this case? Well, actually, if we take a careful look at this design, it happens that A is paired with 2, A2, A2, and A2. And B is always paired with 3, B3, 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 and B3. So this is something bad. This is a bad design. Why? Because the effect of the first factor is totally confounded with the effect of the second factor. What happens? So imagine that we analyze the data with ANOVA and we find that the effect of the first factor is statistically significant. But actually, as this effect is totally confounded with the second factor, it's not possible to know if this effect was caused by F1 or by F2 or by both factors. It is impossible to separate this effect. Well, this is a second example. In this case, more or less, we have the same experiment. And the question is this a good design or a bad design? Well, is anything wrong? Well, so we can see that A is paired here with 2, A2, A2. A3 just appears once here. Okay, so A was tested 3 times at the variant 2 of the second factor and just 1 time at variant 3. Okay, so we just have A3 once. Okay, but here we have B3 just B2, B3, B3. So B3 appears most often than B2. So actually we can say that F1 is basically associated with A, F2 is F1 with the variant 1 is more or less associated with the second variant of F2, and then F1 with B is more or less associated with the variant 3 of the second factor. So there is like a not total confusion within this case. It's not total confusion, but it's partial confusion. So we will say that the effect of the first factor is partly confounded with the effect of the second factor. And this is also a problem. This is not a good design. Why? Because if the effect of the first factor turns out to be statistically significant, we cannot be sure if actually this is because of this factor or in part because of the effect of the second factor. Okay. In this case, so now, is that a good design or a bad design? Here what happens is that we have F1 at level 2 more often than F1 with a level 3. The design is correct, okay, but F1 is tested 6 times at level 2 and 4 times at level 3. It is not very often. It is called unbalanced design, okay. If its treatment is tested the same number of times, it is called balanced factorial design, which is the most frequent case. Just a balanced design is better, except in the case of the variance with the level 2 is higher than the variance of the level 3. So when we have a higher variability, then we may be interested in getting more data to better study the significant differences. But actually, this is not very often. Okay, so now let's count the different combinations. Okay, when the first factor is at level 2, Okay, so we have that factor 2 at the variant A appears 3 times, 1, 2, and 3, and factor B appears, the factor 2 appear with the variant B appears also 3 times, which is 1, 2, and 3. Okay, then when with the factor 1 is at the level 3, we have 2 times with A and 2 times with B. Okay, so this number is not the same. We have 3 times compared with 2 times and 2 times. But here we have that 50% was tested at the variant A, 50% with B. And here we have the same percentage, 50% with A, 50% with B. So as the proportion is the same, we say that the factors are orthogonal. So it is not that these numbers have to be the same. No, this proportion has to be the same. So in this case, it is accomplished. So we say that F1 and F2 are orthogonal. And being orthogonal is the same as saying that they are not confounded, which is something good, which is a good property for any kind of design of experiment. Okay, so given 2 factors, their simple effect will be orthogonal if in each variant of the y, the proportions of the j variants are the same. Okay, well, it's like the formal definition. I hope that in the previous slide the example was a bit more clear. Okay, so if they're orthogonal, it means that it's possible to separate the effect of each factor on the response variable. Okay, which is very important. We always want that this has to be possible. Okay, so now let's think about this example. Imagine that we have 3 factors at 2 levels, and well, we want to check if factor A is orthogonal to factor B. Okay, so this is not a complete design. Okay, because here we have 2 levels. Multiplied by 3 levels is 6. 6 multiplied by 2 is 12. So instead of having tested the 12 possible combinations, we have only checked 6, so half of the complete design. So this is called a fractional factorial design. Okay, some of the combinations were not tested. But anyway, so here, is A orthogonal to B? The answer is yes. Okay, we have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. So this is orthogonal. So is A orthogonal to C? Yes, the answer is yes, because it's 1, 1, 1, 2, which is tested twice. 2, 1, 2, 2 also tested twice. So the same proportion. Is B orthogonal to C? The answer is yes. 1, 1, 2, 3, 2. Sorry. Okay. Okay. So this is something that we have to check in any kind of experiment. Okay. If orthogonality is accomplished or not. In this case, B orthogonal to C. Okay. So we have to think. B to C 1, so B 1, the 2 is combined with 2, the 3 with 2. Okay, so I leave you this with an exercise for you. So in this case, is that orthogonal or not? Okay, so this is something that I put you as an exercise, and we will discuss in the tutorial sessions. Okay, then now. Is the simple effect of the third factor orthogonal to interaction? Okay, so something that we can also study. Okay, so we have the third factor, which can be x or the y, and then the interaction is every combination of the 2 factors. Interaction between f1 and f2. Okay, we are not multiplying anything. Remember, it's just a way to expressing the interaction. Okay, so here. As this is an interaction, so we have 4 combinations. So we have to count. How many times we have A2? It's just once. B and 2, just once. A is 3, also once, and B3, also once. So here we have that 25% of the times we have every one of these 4 possibilities. Okay. So for the third factor with the variant y, if we do the same, we end up having exactly the same percentages. As these are the same percentages, as the proportion is the same, we say that the third factor is orthogonal to the interaction, which is important. Okay, F3 and the interactions are and the interaction is not confounded. Okay, well, now a question. In this design, we can check that. So here, is that a complete design or is that a fractional factorial design? So we have first factor at 2 levels, the second also 2 levels, and also the third at 2 levels. It's a complete design. So we multiply, so we have 8 possible combinations. In this case of complete designs, all factors are orthogonal between them, so we can check that. And also, in this kind of complete designs, we can check that the simple effects are orthogonal to the double interactions. Okay, so as an exercise, you can check that in a factorial plan 2 power to 4. Well, this is a way to say that we have 4 factors tested at 2 levels. So if we multiply, in total, we will have 2 power to 4, which will be 16 treatments, which is 16 values. So in that case, we can check also that the double interaction between A and B is orthogonal to the double interaction between C and D. Okay, and even we could check that the triple interaction is orthogonal to the simple effect. Okay, so this is something that I leave as an exercise for you. Well, this is a design which is not complete. Okay, here we have the first factor at 3 levels, the second also at 3 levels, the third same at 3, the same at 3. So if we multiply 3 by 3 by 3 by 3, this is 91. So in the case of a complete design, we would require 91 trials, but we are just running 9 of them, which is called fractional factorial design. But anyway, in this case, we can check that all simple effects are orthogonal between them. So F1 is orthogonal to F2, F1 to F3. Okay, so all simple effects are orthogonal, which is a very interesting property. Okay, so but what happens with the simple effects and the double interactions? Are they orthogonal? Well, the answer is no. So I leave you this as an exercise. But anyway, so remember that instead of the 81 trials of the complete design, we are just running 9, so just a small part. So just with 9 trials, we have this good property. We can study the simple effects. We cannot study double interactions, okay? But anyway, so this is a good design. Okay, how many trials would have the complete design? So 3 power to 4, which is 81. Okay, so just 1 out of the 9 trials were carried out. So what happens if 2 effects are confounded? Well, so I have explained this before. So for example, the simple effect of A is confounded with interaction between B and C. So it's not possible to separate. So we cannot say if actually the effect is because of A or because of the interaction between C and D. So we don't know. Actually, it's not possible to separate those effects. But we can assume that the effect of A is more important than the effect of the double interaction. Okay, this happens in many cases, but not always. Okay, so we can make this assumption, but this may not be true in practice. So we may have a mistake here when interpreting the results. And what happens if the simple effect of A is confounded with a triple interaction? Well, this is different because in practice, triple interactions may appear, but they don't appear very often. They are not very common. So then we may assume that the effect of A is more important than the effect of the triple interaction. So if this ends up to be statistically significant, so we can assume that this is not important and attribute that all the effect was caused by this factor. Okay, Then, this is another exercise for you. Is this a good or a bad design? It's just short, just with 4 trials. Is this a complete design or a factorial design? A fractional factorial design. This is a fractional factorial design. We have that 2 multiplied by 2 multiplied by 2. In total, we should have 8 trials for a complete design. In this case, we're just running 50% of the trials. But in this case, we can check that all simple effects are orthogonal between them. Okay? In this case, we can check that the effect of F3 is confounded with the effect of the double interaction. But anyway, this is the best possible design with just 4 trials. And here I finished this video about the concept of orthogonality, the design of experiments.